Frisbee. Please join me in welcoming to the Distinctive Voices podium Dr. Charles Isbell.
There you go. So thank you very much for coming. I'm quite happy to be here and quite honored. What I'm going to try to do for the next 45 or 50 minutes or so is convince you that you should care as much about my passion, artificial intelligence, as I do. What I'm really going to do is I'm going to spend a lot of time talking about interactive artificial intelligence. And as you can see by the subtitle here, what that really means is I'm interested in thinking about intelligent agents, systems, machines, whatever you want to call them, that are not just smart but are socially smart. I'm going to try to define for you what that means, give you a little bit of example of what AI is, what it can do, what interactive AI is, what it can do, and I'm going to spend the bulk of the talk going over two examples, two specific points in this space that live up to this notion of interactive artificial intelligence, try to give you some hint of what we are able to do now and what we're going to be able to do in the near term and in the long term. And I hope that by the end of this, I've convinced you that this is something that you should go off and learn more about, and I'm going to stay and answer any questions that you want to answer. Now, the way I want to start this off is I want to define what AI is. It turns out that I don't have a good definition of AI, so I went online and I started searching for good definitions that I thought I would be able to share with you, and I couldn't find a lot of good ones, but I did find a few that I really liked, attributed to multiple people. My favorite is the one at the top, that AI is the art, the science, the engineering of building computers that act the way they do in the movies. I like that one a lot because when you tie it in with the second one, which is that AI is the science, the art, the engineering, and all of the computing that is involved in solving problems that we don't yet know how to do, but humans seem to be pretty good at, you get at sort of what's the strength and the dilemma of people like me who worry about artificial intelligence. The cool thing about those two definitions is they point out that AI is about solving really, really hard problems, solving really cool, interesting things. And the downside is that the moment you understand how to solve a problem, the moment AI actually finds a solution, people stop calling it AI. And so what that means is we can never succeed. There's always a moving target. Once you say, we now know how to do these amazing things, people say, great, that's not really AI because you understand it. Now, I actually think there's a reason for that. I think the reason is that people don't like the idea that one day we'll be able to build systems as smart as they are. And we all want to be sort of mysterious. We all want to be amazing and above all the machines around us. And what I want to try to convince you of, at least a little bit, is that it's okay if we aren't. It's okay that if we're interacting with hardware and we're interacting with software that's about as smart as we are, it can make our lives better. It can make our lives more interesting. The last definition I want to spend a couple of seconds on before moving on is the third one. Now, the reason I like this definition, which is solving exponentially hard problems by sort of cheating in clever ways, is that I think this really captures the essence of intelligence, because I think this is what people do. People cheat in order to get by in the world, and they cheat in two very particular ways that I'm going to try to take advantage of in the rest of this talk. The first way they cheat is that they make assumptions about the world, and it turns out that the world lives up to those assumptions. We assume that the sun is going to rise, that things are going to remain solid, and they sort of do. We also make assumptions about the people around us, and we lean on those assumptions about people in order to make the right decisions by observing others, by interacting with them, getting hints from them about what to do before we make decisions ourselves. And so a lot of what's going to go on in the examples that I'm going to give, the two big examples I'm going to talk about for most of the rest of the evening, it's really about that second thing. It's about understanding people and the smart things around us and leaning on them in order to do smart things. So let me give you a couple of examples of what AI can do, just things that have been developed over the last 5, 10, or 15 years. And what I want to try to get you to see, if you don't already believe this, is that AI is amazing, that we have done and accomplished an enormous number of things in the space of a decade. On your right, or your left over here is a comic book, a graphic novel that was developed by a machine. Took a little bit of input about what it takes to be a story and what it takes to do layout and cinematography, and it built a comic strip. This is work by a colleague of mine at Georgia Tech, a young professor named Mark Riddell, and he's a leading expert in this area. We have cars that can drive themselves in urban areas, in the desert. The DARPA Challenge was about this. They can drive around and they can get from point A to point B without running into anything. This particular car is one of a whole bunch that are out there. This one was also built at Georgia Tech at the Center of Robotics and Intelligent Machines. On the right over there, we have Michael Littman, who's a good friend of mine. He's not at Georgia Tech. He's actually at Rutgers University, and he's demonstrating a piece of artificial intelligence that he built a couple of years ago that can solve crossword puzzles. very good job at solving crossword puzzles. This is actually a machine that competes with professional crossword solvers and does a fairly good job. And Michael himself is actually an expert at this sort of thing. The bottom right over there, the bottom right over there is actually another robot built by Michael and his colleagues, and it learns how to move around and find targets as people go around and pull its wheels off and mess with its actuators and mess with its sensors. It figures out sort of what to do and how to evolve over time in order to solve its tasks. And these are just a couple of examples. One of the more amazing examples that have just come out recently, at least for me, if you wanted to think broadly about what AI is Siri, which was a question that was up there on the screen just before I came up. If anyone has an iPhone 4S, you have Siri, you can talk to it and ask it questions, and it acts as sort of a personal assistant. I haven't played with it, but if the commercials are even half true, it's a pretty amazing thing. Right? We now have a tool on a cell phone which is this big and that thick, and you can say, please tell me what I'm doing today, or help me figure out the closest place to go see a movie, and it listens to your voice, figures it out, it goes out into the web and into the world, gets you back an answer, and tells you what it is. And all this done in the span of 10 years. I personally think it's pretty impressive. What I think is more impressive, though, is answer to a different question. Instead of asking, what can AI do, I want to ask this question. What can AI do with us as human beings? What can it do in collaboration with other intelligent beings, with people? Well, Mark Riddell, who made that graphic novel that I showed you on the previous slide, also builds games, interactive experiences, movies, where people are involved as a part of the movie with other intelligent agents, artificial agents, and they develop a story or an experience on their own. He also does training with this. He teaches soldiers how to react on the field. He does all kinds of things with this stuff. But the point is that some of those people up there, some of those things up there represent people, and some of them represent artificial people. And together they build a story or they build an experience. On the other side of the screen over there, you see Simon, which is a robot built by a good friend of mine, Andrea Tomas, who's also at Georgia Tech. And this is a robot that can do facial expressions, can give you feedback to let you know whether it understands you, try to understand what you're doing, and you can teach the robot how to act. In the center over here is a PSA that was done by Georgia Tech, which shows Shimon, which is a robot that does improvisational music. It listens to the music that you're playing, it gives you cues, nods its head, moves its four little arms, and plays jazz with you or plays marimba with you. There's a bunch of these things that Gil Weinberg, who does music technology down the street from me, does. And these two people are challenging off, and they're playing together. So now we have machines that can solve crossword puzzles, they can drive cars, and they can work with us to build stories, to learn how to walk, and to learn how to play music. This is great, because this means we're finally getting to the point where we can ask the sort of questions that got me interested in AI 30 or 40 years ago in the first place. The sort of philosophical questions of what does it mean to have to deal or to think about intelligent artificial creatures and how they impact the world. There's been a bunch of work recently led by a lot of people, but in particular Ron Arkin, who's a professor of robotics, on what it means to have ethics, what it means for a robot to have ethics. What does it mean to let a robot pull a trigger? What does it mean to let a robot make a decision of when to intervene to help somebody? Can a robot make that decision? Can we blame a robot when a robot goes wrong? And help to sort of build and answer the kind of philosophical questions. We've finally gotten to the point where that's no longer science fiction, but it's fairly close to being science fact. I think that's great. So this brings me to interactive AI. So here's what I want to claim interactive AI is, given that sort of background and context. Interactive artificial intelligence is the science, it's the art, it's the math, it's the computing of figuring out how to build autonomous systems, agents, artifacts, that have to live and interact with other intelligent beings, some of whom may be human. Now, it turns out that it's important that some of them are human because it means we can't just have the little robots talk to one another over wireless. They have to figure out how to interact with people. It also means that because they are possibly human, they have their own goals, they have their own desires. They might conflict with what the robot needs. But it also means we have to understand what it is that the human wants, what it is that the other intelligent being wants, and we have to somehow adapt to that over time. Now, when you think about it this way, what does it mean to build an intelligent thing, not just that can play chess, but an intelligent thing that can learn how to play any game you want to with somebody, invent a game, create a game? You realize there are a lot of things that that intelligent system has to have. I'm going to claim that these are a few of them. It has to be persistent. It has to live more than the length of a day or the length of how long it takes to solve some crossword puzzle. It has to live for years and years and years. And if it's going to live for years and years and years, it needs to be adaptive, because the world is going to change in that time, and you're not going to be able to stop, let someone come in and reprogram you for a couple of weeks and figure out what's going on before you move on to the next thing that's going on. And if you're going to be persistent, if you're going to be adaptive, if things are going to change over time, then by necessity you're going to have to be collaborative. You're going to have to be able to interact with other intelligent beings to solve the things you need to solve. You're going to have to learn how to compromise. You have to learn how to communicate your needs and to understand and infer the needs of others so that you can accomplish whatever it is you need to accomplish. Or even to understand what it means to accomplish something and what things you might need to do over time. Finally, the things I want to mention today, I think it's important that it be believable. If you're interacting with not just intelligent agents, but with humans, it turns out that humans very much want to believe that what you are is an intelligent thing. There's a lot of science behind this. I won't be able to talk about it tonight, but it matters a lot that you act like a being with intention. If you act like a being with intention, humans are willing to treat you as such and to give you the benefit of the doubt. Now, I think that if we can make progress on building systems that are persistent, adaptive, collaborative, believable, buildable, scalable, then we'll be able to build machines that can work with humans to accomplish great things, whether it be music or medical procedures or anything that you can imagine. And then furthermore, these systems that we build will be robust to all the changes that are going on, including changes that we can't possibly anticipate, and that eventually they'll be able to coexist with us as humans as long-lived partners and live with us in harmony, as opposed to the alternative, like rising up and killing us all. Now, what I'm going to do is I'm going to talk about two examples in this space. Okay, I'm going to go into a lot of detail about them, and I'm going to spend about half an hour on them. The first is a system called Cobot. It's a socially situated agent. I'm going to define what that means for you in a couple of minutes. But basically, it learns how to be a socially reasonable actor. And I'll define that for you as well. The second is a class of systems that others, people like Mark Riddell, people like me, build, called interactive fiction, drama managers. Things that build stories, that work with authors and work with players to build experiences that people find aesthetically pleasing and useful. And what's going to be interesting about this, is differentiated from Cobot, is that these are systems that try to convince you to do what they want you to do without you knowing about it. And I think that's, well, we'll see when we get there. Okay, so let's talk a little bit about Cobot. So here's the sort of one-page takeaway of Cobot, and I'm going to use a lot of terms that I'll define later, and I hope you bear with me. Cobot is a social statistics agent. And what that means is that Cobot builds statistics about all the social relationships that are around him, and I'll define exactly what that means for you in a moment. Interacts with humans in a complex and real virtual world, and I'll tell you what that world is in just a second. Models all the individuals in that world and the behavior and interrelationships between the individuals in that world, and adapts itself accordingly, modifying its behavior over time in order to accomplish some goal, and uses a lot of math tricks to sort of make it all go through. Now, this is the world that Cobot lives in. He lives in a place called Lambda-Mu. Has anybody here ever heard of Lambda-Mu? No? So it's a pretty famous virtual world 10, 20 years ago. It's a multi-user text-based environment. So it's like IM or IRC or any sort of these kind of chat worlds you might have interacted with or might have seen others interact with, except it's sort of special. And it's special in a bunch of ways. One of the ways that it's special is that the people who live in this world don't just talk one to another, but they all talk to each other. Thousands of people in the same space simultaneously talk to one another, and they create the world as they go. So rather than being a sort of fixed space, a fixed topology where people sit and they talk to one another and they move around, the users themselves can create rooms, what they're called, new spaces. And they can give them any sort of properties that they want. They can create objects like butlers or cars or seats and talking sofas, whatever they want to build. And those objects persist even when they're not logged on and they've gone away. Furthermore, they can create their own behaviors. They can decide that the correct way for people to interact with one another is to wave, or the correct way is to bow. And they can define what that means, and they can share that notion of behavior, the sort of code that's behind that, with each other. And that turns out to be a very powerful thing, because what we have now is an environment full of very interested people who are creating the world as they go, constantly changing, constantly persistent, and it leaves a space even after the people who created them are long gone. It was founded in 1990, and as far as I know, is the longest still running Mu in existence. At the time that this work was done, sort of at its peak, it had over 4,000 users spread across the world. At any given time, several hundred of them were on 24 hours a day. It had over 120,000 different objects that had been created by the people who live in that world, and over 2,000 rooms that had been created. And in fact, we know that there are several thousand rooms more than that. Those are just the rooms that I was able to find with Cobot that I was allowed to get into. But there were thousands and thousands of these rooms that were created, thousands and thousands of these objects, and thousands of people doing them. Now, the population was sort of technologically sophisticated. They had to be. This is 1992, say, and you're able to log into a computer and build little objects in rooms, so you had to have some technological sophistication. But at the same time, some of these people were computer scientists and engineers. Some of them were sociologists. Some of them were 14-year-olds. Some of them were 75. Some of them were 23. They had a whole mix of attitudes towards the place and reasons for being there. And so, in fact, what was interesting about this, and what I think is really kind of crucial for this notion of interactive artificial intelligence, is that they had a strong sense of social community. These were people who were friends. They were friends in real life, they were friends online, and you can't really characterize why they were there or what they were doing at any given time. This isn't a virtual space where people come to have a meeting and to talk and to solve some specific problem. This is a place where they come to talk about sports, or they come to talk about politics, or they come to talk about sex, or they come to talk about whatever it is people get together to do. And you don't know what it is that they're going to talk about when you walk in the room. So you can't build in all of those assumptions. You have to learn them on the fly. So that's the world in which I'm going to drop a little virtual bot that's going to try to figure out how to navigate this space with thousands of people from different cultures across the world making it up as they go along. Now, if you walked into Lambda Mu, this is the sort of thing that you might see. You might walk into the living room, and you might see HFH and Buster talking to one another. Now, I'm HFH, by the way. Buster is one of my colleagues, a guy named Michael Kearns, who's now at UPenn, and we used to spend a lot of time in Lambda Mu together. And here's the kind of conversation that we'd have. I would walk in, I would wave to Buster, Buster would bow gracefully to me in return, would complain about something going on in his life, and I would comfort him and we would move on. Now what you actually see here are a bunch of verbs, a bunch of commands, a bunch of text that's going on that kind of describes the everyday interaction of Lambda Mu. Up there I waved to Buster. I didn't type in like you might in an IM chat, wave to Buster. I just typed wave Buster, and it generated all of the right text. I saw you wave to Buster, Buster saw HFH waves to you, and anyone else who happened to be in the room saw HFH waves to Buster. When I bowed gracefully, it wasn't something I typed out. I actually used the bow verb, which someone else had created for me, and if I didn't like, I could have changed. I directed speech to Buster, and Buster responded to me, and sometimes responded to the room, and it was all visible. This is sort of an ongoing story, an ongoing textual social interaction that anyone could sort of watch. And there are all kinds of things that are going on there besides waving and hugging. You could drop anvils on people. You could zap them with static electricity. You could smile at them. You could do almost anything that you can imagine. And in fact, it turns out that one of the reasons we chose Lambda Mu is because it was just text. So I showed you a lot of nice pictures of robots and cars and people doing all kinds of things that were physical, and those are very nice and visual. But the nice thing about text is you can say, I've decided that I am a green blowing gas, and it's perfectly fine. You don't have to worry about how that animates. You don't have to worry about what happens when you move from one room to the other. You can basically just use your imagination to describe it, and people can use their imagination to understand what it might mean. And so that actually turns out to be a fairly powerful thing. So here's what Cobot looked like in that space. He looked like a user. He looked like any other player, as we used to call them at Lambda Mu, but was known to be a robot. It was in his name. It was Cobot. We didn't try to fool anybody, although we did manage to fool a few people accidentally. We weren't trying to. If you looked at Cobot, he would say, I'm a robot. There are wires sticking out of me. I'm not quite finished yet. If you have any problems, go talk to HFH. Okay? So I wasn't trying to do that. He spent most of his time in a place called the living room, which at the time was a very big social hotspot there. There was roughly one event generated in the living room every 11 seconds. 365 days a year, 24 hours a day. So that's a lot of activity to sort of absorb as it goes by. Now, Cobot's primary functionality, at least at the beginning, was to observe everything that happened in front of him and to build models of what he happened to observe, and to build statistics and allow people to ask questions about socially what was going on there. So let me give you an idea of what that means. So when I waved at Buster at the beginning of that little transcript before, well, I typed in wave Buster. And what everyone saw was HFF waves to Buster. But what actually happened is a little command was sent to every single object in the room. And Cobot, being just another object in the room, just like I was, just like Buster was, just like anything was, could actually stop that command, look on the stack, and sense without error who typed in the command, what the command was, and who the target of the command was. So Cobot could figure out, without having to do anything difficult with sensors, who was doing what to whom under all circumstances. Which meant Cobot now had a notion of all the social interaction done in front of him. So he knows every verb, every command that was invoked by a particular user, any particular user who ever interacted in front of him, which gives you some notion of communicative style, right? Some people like to hug, and some people like to kick you in the shins. He also knows all the verbs that have been executed on a person, which gives you some notion of sort of the community treatment of a particular individual, because some people are hugged and some people are kicked in the shins. And he also has a notion of all the people that you interact with and what your social circle is, and knows how every verb is used by whom and for what reason. Now, this turns out to be very, very neat, because as a computer scientist, it means I can represent every single person around me as a little point in a ridiculously high-dimensional space, and then I can just do math on them.
What about gender?
Gender you could also find by looking at an object, and the object will tell you gender, but it doesn't really tell you anything, right? The question was, what about gender? Well, what about gender? I could look at Cobot. Cobot, by the way, was a boy. Is a male, and there are very particular reasons why that is that I do not want to commit to tape, so feel free to ask me after the talk is over. But there were very specific reasons why Cobot was male. We never really used that, although we could always determine it because we always knew who everyone was. But the key point here is that everyone was a little mathematical object, which has always been my secret fantasy, and you're able to sort of move around and compare people that way. And I want you to think about what that means. I want you to think about what it means if every day you go home, you could take out your iPhone, pick up Siri, and say, tell me what's going on. Tell me how my boss treated me. Tell me how my so-called best friend interacted with me versus that other guy. And think about what that would do to the way you interacted in the world. This is the sort of thing that you could ask Cobot. So here's an actual interaction that I had with Cobot. I said, relate me to Buster, my good friend Buster. And here's what Cobot told me. He whispered it, because I asked him to, and because you don't want to spam the room. He said, here are your relationships to Buster. You like to use dash, that's a directed speech. 62% of the time, you like to poke, hug, eye, warily, nod knowingly, give high fives, zap, comfort, and grin with one another. A very sort of testosterone-driven relationship. You will notice that Buster is number 14 on my list of playmates. That is, there are 13 other people I interact with more than I interact with Buster. But I'm number 1 on Buster's list. So we know where the power dynamic is there, don't we? Our socializing overlap is pretty big. It's 75%. We only share about 33% of our playmates together. Our actions are remarkably similar, and we're treated remarkably similar to one another. Which tells you a lot. I can ask Cobot, tell me about hugging. Tell me who hugs the most, who is hugged the most. Tell me how I compare to everybody else when it comes to hugging, or it comes to being kicked, or it comes to swimming, or it comes to grinning, or it comes to any of the other things that you can do. I can even ask Cobot, well, who is like me? Well, since I'm just a point in some mathematical space, and everyone else is a point in a mathematical space, I can measure distance. There's a great story, at least a story I find really nice. There's this thing in Lambda called illegal seconds. So it turns out that behind your character, HFH or Buster or whoever you are, there's really just an email address. So I own Isbell.org, which means I can generate as many email addresses as I want to. And it turns out people really did this. People would create different email addresses and then therefore create different accounts. And they would pretend to be different people. Speaking of gender, so people would come in and they would be male, or they would decide to be female. They would pretend to be friends with one group of people or pretend to be friends with another group of people. And people would do this for years unknowingly. A good friend of mine on Lambda came up to me one day and said, I went up to Cobot and I said, tell me people who are like me. And I got back a list of all my illegal seconds. Which means that even though he'd been fooling people for years about the 7 or 8 different folks he was, he didn't fool Cobot. And the reason he couldn't fool Cobot is because at the end of the day, you have tropes, you have habits, you have tics, things that you do, and Cobot was able to pick those things up and therefore determine that all the people who are like him actually happened to be him. Now, it turns out that when you give people this power, when you give people the power to kind of ask these questions, it actually affects the world around them. So here's a couple of conversations that sort of went through. The names have been changed to protect the innocent. Rain is talking to Cloud, and he says, Cobot says you act like me, and I want you to stop. So I don't like the way that you're acting if you act like me. People started playing games with one another and getting angry with one another if they were ranked higher or ranked lower on their list compared to other people. And people really started changing their behavior as a result of this, simply because they were able to determine without any sort of error what the social relationships and what the hierarchy was. People began asking questions of one another. They began trying to figure out how to be the cobot's favorite friend and sort of so on and so forth. And it really changed the behavior. It actually changed a lot the number of interactions that were going on, how people interact with one another, and so on and so forth. It did lead to a problem, though. Now, all I've described to you so far is that Cobot sits there and he looks at you and models you. But that's all he did. If you tried to talk to Cobot, Cobot didn't say much if you didn't ask him a specific question. And in fact, if you asked him something he didn't understand at all, he would say, go talk to HFH. And it turns out people don't like that. It turns out that if there's a little creature sitting in the room that just sits there all day, 24 hours a day, determining everything that everyone does, people start to get suspicious. Started accusing me of trying to figure out from their behavior patterns what their social security numbers were and things like that, which, sure, why not? I mean, if I could do that, great, but I can't. And so we had to figure out something to do. And so what we decided the most important thing was, in a place like Lamnamu, was being able to talk. And so we tried to come up with some clever way to allow Cobot to talk. Now, this is good news because it means people cared. It was bad news because there was no way that we were going to solve the natural language understanding problem in a couple of days. So we cheated. What we did is we started out by trying to hand code a bunch of interesting things. I sat there and I came up with all kinds of clever responses to things that people might say to Cobot. If you kick Cobot in the shins, he would say something like, you'll be first up against the wall when the revolution comes. But I can only be so funny for so long, and I had to come up with something else clever. And what we all came up with together was reading. So what we did is whenever someone talked to Cobot and didn't ask him a specific question, he didn't really know what to do with it, he went off and he read some document. He took the words that you spoke at him, he compared it to sentences in that document, and then found a document that had a lot of words like that. You know, just kind of Google, what we would now call Google searched over sentences, and did it. And we asked him to read only very specific documents. So the first document we asked him to read was the Unabomber Manifesto, which, if you know anything about the Unabomber Manifesto, was hilarious. Because what happened is you have this little intelligent technological thing running around, and you would talk to it, and it would yell at you about how all technology was evil. So that was good, and it worked really, really well. By the way, the Unabomber Manifesto is very nice for this sort of thing because every sentence is a topic sentence. It's highly didactic. You sort of can't go wrong. There aren't a lot of short sentences in there that don't mean anything. There's a lot of long sentences in there that don't mean anything. And it's very, very specific, and it's very, very good. So we went with that. We did the script from Planet of the Apes. We did all kinds of, we did the works of Rilke, who's a German poet from a couple of centuries back. And we just had Cobot talk like that. And it turned out to work. People would engage in long arguments with Cobot over technological matters and would lose because Cobot would go on and on and on and on and would usually win. I really like this one. After a long conversation about veterinarians and the Roman system of urban sanitation, Cobot declares that he is an intelligent being and people treat him wrong. That's taken directly from Planet of the Apes, by the way. But by the way, there's actually a trick in here. So they don't all look like this. If I showed you all the transcripts, which I couldn't do, but if I showed you all of the transcripts, you would see there's a lot of non sequiturs in there. But people seem to only remember the ones that made sense, which tells you something about people when they sort of want good things to happen. But there was actually something else going on there, is that people would help Cobot. Are people here familiar with the Turing test? So the Turing test, for those of you who don't know, is Alan Turing, who is sort of the father of computer science, said we'll know when we built intelligent machines when you can put a person behind a computer and have them talk to someone that might be a person or might be a computer, and they can't tell which. They can't tell if they're talking to a person or talking to a computer. There's lots of things wrong with that, but it's a sort of interesting kind of thought experiment. So what we kind of thought about here is that this is really a notion of the kind of assisted Turing test. What happened is that after a while, if you think about the algorithm that I gave you for finding sentences, Cobot had to take the words you said. He had no memory. So he didn't remember everything you ever said. He just remembered the last thing that you said. That's called the Markovian assumption. And so people started talking to him in sentences. When they realized that talking to him in short sentences didn't result in answers that made any sense, they would start talking to him in longer sentences. They would keep him on topic by remaining on topic themselves and not taking the shortcuts that we all take for granted. By the way, as far as I could tell, they didn't notice they were doing this. They just started to do it in the same way that you change the way you talked to a 4-year-old or the way you talk to a 15-year-old just by interacting. It's what people are exceptionally good at doing. right? Negotiating with one another how they're going to communicate and then adjusting accordingly. And people would do this with Cobot, which I thought was sort of great. Now, this brings me to one slide I want to show you about this. It's not meant to be terribly visible, but what's on the x-axis is time, and what's on the y-axis is cumulative interactions. And I'm going to show you this because I want to show you one other thing, and I need you to know that Cobot was popular. So this blue line here that you see starting out low and going up is the total number of interactions that Cobot had, accumulated over time. And you'll notice that in the beginning when Cobot didn't do much but sit there and I was debugging him, people would poke him every once in a while, and there'd be this kind of steady growth of interactions. And then as soon as he could start doing social statistics, he took off. People started interacting with him a lot. The moment that he could start emoting and doing simple chatting, people would deal with him a lot. And then the moment he could really hold a conversation, it shot up through the roof. And by some measure, he turned out to be the most popular entity, at least he knew about, in Lambda. This green line, by the way, is me. And at some point, Cobot became more popular than me, which I've learned to deal with over the years, mainly by shutting him off. But in any case, you'll also notice if you look very, very carefully, at every jump, there's this sudden jump. It goes down a little bit, but it never goes back to where it was. And that says that there was some long-term effect of these abilities that people found useful or interesting or entertaining. So Cobot is popular, which means we've got thousands of people interacting with Cobot a lot, which means we've got a lot of data. And there's an interesting question to ask yourself, which is, well, is there anything to this data, or is it just, a lark, something that I got someone to pay me to do for a little while? And the answer is, it turns out it's not just a lark. So I'm about to show you a graph. It's not going to be terribly visible because I just don't have the resolution on this screen, but let me tell you what the graph represents. Every node on this graph that I'm about to show you is a person. There's actually going to be thousands of nodes up there. Every node has a color, and the colors represent something about commutative style. So it's an HSV space, V is held constant, I can't remember what H is, I can't remember what S is, but one of those dimensions of color represents sort of the number of events that people generate, and another represents the kinds of events they generate. Do they speak a lot, or do they use the other verbs besides speech to communicate with one another? And so therefore, similar colors represent similar styles. Now this isn't just a graph, it's a directed graph. So there's an edge from some node A to some node B, if and only if B is in the top 25% of all of A's interactions. So if I have a lot of incoming edges, which is called being an authority in graph theory, then it means a lot of people interact with me, or I interact with a lot of people. If I have a lot of outgoing edges, then it means I interact with a bunch of people equally. Okay, that's called being a hub in graph theory. And this graph is going to allow us to notice a few things about what's going on in Lambda. Now again, you can't see the arrows, it's not terribly visible, but I think even from where you're sitting, you'll notice a couple of things, at least once I point them out to you. One thing you'll notice is that there aren't a lot of different colors. There's about 8 to 9, depending upon how you kind of define what similar colors are, and that's not just an artifact of the projector. It turns out that basically there's only 8 or 9 different kinds of people of the thousands of people interacting in Lambda, at least by this measure. You'll also notice, at least if you walked up here on screen and looked very carefully, that there's a few people in the center of what kind of looks like cliques. These people have a lot of incoming edges. It took a very smart grad student, a guy named Kristen Shelton, who's now a professor at UC Riverside, to figure out how to generate this graph in a way that showed. It turns out it's its own research. You could spend hours talking about how to do graph display. And he spent weeks and weeks working at it before he got it to sort of display the structure this way. Now I want you to look, and you'll notice that if you point into the center of these little cliques over here, like that one there, and that one there, and that one there, and that one over there, they look green and blue, as opposed to purple and yellow. If you look very, very carefully at this graph, you would actually notice that all the people in the center of those cliques, that is the people that have a lot of folks interacting with them, are all colored differently, and they actually all point to one another. There's about 11 of them. They're the 7 degrees of Kevin Bacon of this graph. If you got rid of them, the entire graph would collapse. So the most popular people in Lambda all act differently, and they all know each other, just like high school. You never, ever leave high school. And the people who do this sort of thing for a living tell me that this is just the way social graphs always look, eventually. If you get enough data, you get enough people interacting with one another, you get things that look like this. You get things that look like high school. I mean, there's a reason high school is the way it is. Now, I'm showing you this, one, because I actually think it's a beautiful piece of art. I actually have this hanging up on a wall outside of my office. It's sort of 5 foot by 6 foot. It's beautiful. But also because it reveals something important. It reveals that there's structure. structure to the social interactions of these people, even in a place like Lambda. And if there's structure, then I can learn it. And if I can learn it, then I can leverage it, and I could learn to act better. And that is exactly what we did. We built a system that would be proactive. Everything I've described to you so far about Cobot has been reactive. This is proactive. So Cobot tries to figure out now, for the rest of the next couple of slides, how to do complex social actions in a space like this. How to take feedback, social feedback, from the users around him in order to change his behavior, in order to be sort of socially optimal, at least by some definition. So this turns out to be an experiment, and a pretty interesting experiment, in sort of multi-user collaboration in training some social entity to act appropriate and proper in a particular community and particular culture. Now, I'm going to very quickly run through 2 slides, which is the technical content of Cobot, about how we did this. We used something called reinforcement learning. The only thing I want you to get out of reinforcement learning is that it's a very particular way of looking at the world. It says the world is made up of states, that is, things that describe the way the world is. It's made up of actions, the things that you can do in the world. It's made up of some model which tells you how, when you're in some state and you take some action, where you're going to end up. And it's made up of rewards, that is, signals from the environment that tells you whether things are good or things are bad. If I move over here, things are good until I stand in front of the projector and I can't see, and that's a bad signal. I move over here, suddenly I can see, and that's a good signal. Okay? And the goal of reinforcement learning is to learn a policy. And all a policy is a function that maps states to actions. It tells you, for whatever state you're in, here's the action that you should take. And the optimal policy is the one that maximizes long-term expected reward. That is, it tells you what you should be doing now so that if you keep following the optimal policy, you will end up happier at the end of the day, at the end of the year, at the end of the decade. This actually turns out to be a subtle and important thing because it allows you to make decisions that locally look bad but end up in a good place over a long time, like going to college, right? It doesn't make any sense to go to college because it costs you money, but by going to college 4, 5, 6, 7, 8, 9, 10 years from now, the world will be better for you. And reinforcement learning lets you do it. It's very well defined. It's very well understood. It's an enormous amount of work out there. A lot of success. The best elevator algorithms, or some really good elevator algorithms, have been learned through reinforcement learning. We know how to play. People have used it to play robot soccer, to build backgammon games. It's just amazing. There's all kinds of things that we know how to do with it. But it turns out that reinforcement learning, as great as it is, as much as I believe in it, doesn't really work in this world. And the reason it doesn't work in Cobot's world is because everything about the social world of people violates all of the mathematical assumptions that we've been making. We assume that we can ignore history when we deal with reinforcement learning, and we have something called the Markov assumption. We assume that there's lots and lots of data. And it turns out that while one event every 11 seconds seems like a lot of data to you and me, it's nowhere near enough data to solve the kind of problem that we're trying to solve. People are, you may have noticed, inconsistent. They are noisy. They change their mind over time, so they're called non-stationary. And there's a very specific thing, besides these kind of minor technical details, that makes this problem interesting. And that is, the way I described the reinforcement learning problem to you before is I said there was a signal from the environment. There's the light shining in my eye. But in this world, there's not a single light shining in my eye. There's 100 lights shining in my eyes. And they might all want different things. And I have to figure out some way to combine them. Let me give you an example of how that might be hard. So let's imagine that I'm Cobot, okay? And I've only got 2 things I can do, A and B. And let's say that you really, really like A and you really, really hate B. So what would be a reasonable thing for you to do? Well, a reasonable thing for you to do as you're interacting with me is to reward my A's and punish my B's. And that way I'll learn to do more A's. And I think it's pretty simple how you might do something to do that. And let's say you walk into the room and you, more egalitarian, you want to see things being roughly the same, so you want the A's and B's to happen in basically the same, same frequency. So what's a reasonable thing for you to do? Well, a reasonable thing for you to do would be to punish the A's and reward the B's to bring them back into balance. And that would work. Except what happens when he leaves the room and I'm left with him? What do I know about him? What I know about him is that he hates A's and he likes B's, but that's not true. He liked them equally. And the reason I got the wrong idea if I treated him in isolation is that I forgot that he was basically competing with someone. So it turns out you can model parenting, multiple parenting, as people competing with one another to get across their idea of what the right thing to do is. And if you do that, then you can change the signal into something that actually tells you what they really want when other people are in the room and what they really want when they're alone. And that's what we did. And so we built a a little reinforcement learning agent that took risky social actions. Now remember, this is very risky because we're in a social world, and if Cobot irritates everybody, they just stop talking to him, right? And I can't run the experiment again. So these are risky social actions, interrupting people, introducing them, trying to play games, or so on and so forth, making social commentary, these sorts of things. Taking state in the world that's all social and trying to figure out what to do. And we ran this for several months. We got about 63,000 actions taken. We had 250 people interacting with us and 3,000 pieces of social feedback. And it worked. It turned out that Cobot, just by interacting with people and watching the way they dealt with one another and dealing with both the explicit and implicit social feedback, was able to learn how to maximize its long-term reward. It was able to act as an appropriate social actor in a world of competing social interest and ever-changing culture. And it changed over time, as it needed to change over time. And it learned that when he left the room, to act differently. And that was pretty good, because it meant that we actually managed to get some creature that was a significant member of a social community, lived in a complex social environment, provided a service that people actually found useful, was able to become popular, and was able to learn. And in fact, because it had this notion of how people felt about him and how the world would change as he changed his behavior, he even had a notion of emotion. If all the people who didn't like him came in the room, and you asked him how he was doing, he says, "I feel sad, and it's never going to get any better." But if one of his friends came in and you asked him, "How do you feel now?" he'll say, "I don't feel pretty good, but things just got better." And that wasn't because I hand-coded into him this notion. It's because his view of how his long-term reward was going to be changed when someone who gave him positive reward came in the room. Now, what I wanted you to get from that is that even in a world with thousands of people with competing social interests, we can build systems that can actually learn how to interact socially with people. And now I want to flip this and talk about something slightly different, but of course related, which is this interactive narratives notion. So we built a bot that was influenced by his environment, influenced by people, and of course had an impact on that environment, but that impact was incidental. I want to build something that actually can change what people do on purpose to some specific goal. Because that's what you're going to want to do if you're going to have to interact with other people. You're going to want to convince them to take on your desires and your goals in a nice way, but you're going to want to convince them to do that. And the way that we're going to do that is through interactive narrative, through game. So what I mean by that, same picture that I showed you earlier, is I want to just build a world, just a game. And instead of having, there'll be bots in it, just like Cobot. There'll be people in it, just like you. You'll interact with one another. The bots will try to make decisions. And there'll be something that tells the bots what to do in order to get you to have a wonderful experience. So I'm going to talk about building some kind of software environment that allows people to interact and to change that environment and to affect effectively a story. And that's all I mean by narrative, is a story. Now there are lots of these things out in the world. At least when I was young, there were a bunch of choose-your-own-adventure books. This is basically what I'm talking about. You get to make a decision for a story, and that affects the outcome of the story, except now it's virtual, and you're interacting with thousands of other people, or you're interacting with thousands of other artificial agents. And it turns out that this notion of narrative, this notion of story, is actually central. And the reason it's central is because everything's a story. Everything is a sequence of events that lead to some events that are good and to some events that are bad. And so this is kind of a central idea. If we can figure out how to change the story, then we can figure out how to influence the world and influence the people around us, presumably and preferably in a good way. So let me convince you first that this is a hard problem, and then convince you that I solved the hard problem. So is it hard? Well, it's hard for two reasons. I'll give you the easy one first. It's hard because there are a lot of stories. If I told you I want you to read this choose-your-own-adventure story, and you can do anything you want to at any given point in time, that's a lot of stories. And if some of those stories are good and some of those stories are bad, and I'm trying to convince you to have a good story, a good experience, that's a very hard problem. In fact, it's hyper-exponential, which sort of means that if the story is of any length, there's no way to look at all the stories. And in fact, for some of the stories that we look at, if every atom in the universe were a printer, printing out 1,000 different stories a second, you still wouldn't be able to print out all the stories before the heat death of the universe. That's a lot of space to search. So it's hard. It's hard just because there's a lot of options. But it's also hard because there are subtle things going on here. Imagine I was trying to build a mystery game, right? We're going to do some kind of murder mystery. So what happens in a murder mystery? Well, you walk into some house, when somebody gets murdered and you don't know who it is. That's why it's a murder mystery. Then you sort of move along for a little while and you discover that every single person in the room has a motive. And you're pretty sure it's her. And then she gets killed, and so it turns out it's not her. She was a red herring. And so then you learn something else and something else. There's a big reveal, and then at the end, at the very end, you figure out it was the butler all along, right? And that's a murder mystery. And it has its own rhythm, right? It has its own cadence. And good murder mysteries all follow that sort of style, but they do it in a very particular way. Now let's imagine I'm allowing you to decide what happens in that murder mystery, and you walk in the room too soon and you see who killed, who did the killing. Well, then it's no longer a mystery. And by the way, if you run away and that person keeps killing and killing and killing and killing in a slightly different speed, then now it's a horror story. And it doesn't take much to move from a murder mystery to a horror story. And if I wrote a game that I wanted to be a murder mystery and you turned it into a horror story, then there's a problem. So the question before us is how are we going to be able to create an environment that allows you to explore and do everything you want to do on the one hand, but still guarantee that it'll be a murder mystery rather than a horror story at the end of the day? And it turns out the answer is use the same kinds of things that we did before. Use the same kind of technological solutions we used for Cobot, use reinforcement learning and all the tricks that we did then in order to figure out how to intervene, how to take appropriate actions in order to get you to do what I wanted you to do. And we did that because we're very smart people and we were very clever and we just knew we were going to solve the problem, and we did solve the problem, and in fact, we solved it a little bit too well. And what I mean by solving it too well is we built systems that would allow you to play these murder mysteries or to play these games, and we made damn sure that you had a great time. In other words, we found the best story for you to have, and that is the story you had. And it didn't matter what you tried to do. And it turns out that isn't really what people want, because it takes away their autonomy. It takes away their self-agency. There's actually a term for this. It's called playing on rails. If you've ever played any video games where the designer of the game wants you to go through a particular door and you don't want to go through that door, the game locks every other door. And you can't leave until you go through this one door. And it takes you out of the game. It takes you out of the experience. It takes you out of your ability to have agency. And that's not really sort of the right thing to do. We've got to come up with some way to influence you to do sort of the right thing. And so we have to back off this notion of saying this is the murder mystery we want you to have and allow you to still have some notion of agency. How are we going to do this trade-off? Well, it turns out the trade-off involves two technical tricks. I'm going to skip the first technical trick and talk about the second technical trick, because I think that's the thing that really gets to the heart of interactive artificial intelligence and is what I want to end on. So trick one involves rethinking reinforcement learning just like we did before, and involves lots of equations. Now, by the way, when I learned how to give talks, I was told by my advisor that you always have to have at least one slide with a bunch of equations on it that nobody understands, and that you don't explain, because that's how they know you're smart. And you know I'm really smart because I have two of them, and I use really, really tiny font that I'm guaranteeing you can't read. So that math is actually real. I didn't just make it up. But it really doesn't matter. The point is, there's some technical trick you have to do. It's actually a very clever technical trick, but there's some technical trick that you have to do that involves a lot of math. And the bottom line story is, it turns out I can solve this hyper-exponential problem that I don't have enough time in the universe to search over in time that's effectively constant, if I'm very clever and I use a lot of math. But that's not very interesting. What's actually interesting is the second technical trick. This is what I want to talk to you about in the last 10 minutes. The second technical trick is to say, you know, the job here, if I want to get you to have a good story, I want you to have the story I want you to have, instead of intervening and locking all of the doors so that you can only go through a good door, I should instead convince you that you want to go through that door. And if I convince you you want to go through the door, then you're still in control, or at least you still have the illusion that you're in control. And so what we're going to do is we're going to go out in the world and we're going to figure out ways that we can trick people into thinking they want to do what we want them to do. And we're going to steal stuff from behavioral economics, and we're going to turn this problem of intervention, of action in the world, not from one of locking doors, but from one of influence. And we're going to adopt, for the purposes of this discussion, a particular set of ways of doing influence. We're going to sell the player the goal. So we're going to convince you that you want to have the murder mystery we want you to have. And the way we're going to do this is we're going to implement something called click-whir responses. People know about this. So I didn't actually know about this for a long time. Click word responses are effectively what you would call reflexes, social reflexes. So, we all have physical reflexes, that whole, hit you on the knee and then your leg does that thing. Those are physical reflexes. You put your hand on something hot and your hand goes away, and you have to work very hard to overcome those reflexes. But there are also social reflexes. So there's this fish, I can't remember what it's called, but there's this fish that swims around. It's got teeth, and it goes around and it eats other fish. But it turns out that there's a little space where you can tickle it that makes it open its mouth. And so there's this specific other kind of fish that has evolved over time or something, so that it tickles that little spot, which makes the fish open its mouth, and then the fish go in and they eat all the food that's stuck between the fish's teeth. Which I know that sounds gross, but the point is the fish get food. And by the way, the fish that opens its mouth, he wanted to open his mouth. That's what he thinks, or at least that's what people think he thinks. It was his idea. At least he thinks it was his idea. And this is what we want to do. I want to get you to open your mouth so I can pick the food out of your teeth, metaphorically, and convince you it's your own idea. So here's 6 ways that people do this. And this is stuff that you can take out of the behavioral psychology literature and marketing literature. And I'm just going to very quickly go through these. A couple of them I just think they're just amazing. So reciprocation is the notion that people, if you give someone something, they usually feel obligated to give you something back, right? So you offer someone something in one context, they kind of feel compelled to kind of give you something in return, at least if you do it right. Salesmen do this all the time. If there are any salesmen on it, you know you do this all the time. Consistency is my favorite one. Consistency is one where it turns out you can get people to say things out loud. They feel this almost pathological urge to at least appear consistent. So here's a trick. So I know California doesn't have as much grass as Atlanta does, where I'm from, but we all have yards, and I live in a subdivision, and there's some people who just don't mow their lawns. You know how they are. You can get them to mow their lawns by yelling and screaming at them. Actually, it usually doesn't work. They just kind of dig their heels in, and they don't mow their lawns. And if I were playing a game where I was trying to get you to mow your lawn because it was a crucial part of the game for some reason, if I were going to do this on rails thing, what I would do is I'd set up walls. You just can't leave your yard until you mow it, which isn't the most fun and interactive and immersive game you can imagine. But here's the alternative. Here's the trick you should use on your friend who doesn't mow his lawn. Go in the winter. California has winter, right? Go in the winter, and when the grass is already cut low, and say, doesn't the grass look great when it's all the same size? Just talking casually, bringing up your conversation about lawns in the winter. Just talk casually about it. And when he says, yeah, it really does look nice. Next summer, he'll mow the lawn, and he'll think it was his idea, because he has to be consistent. Now, there's more subtleties to it than that, but it's really that simple. If you do it right, you can get people to be consistent, at least out loud and in public. You get people to say something, they feel compelled to stay that way. Social proof is simply the fact that people look to other people they feel are like them in order to determine what to do next. I think you've all been in a place, you've walked in a room, you weren't sure what to do, you found the person you thought it was most like you, figured out what they did, and now you know what to do. Liking is just, you're very nice to people you like. Authority is you tend to do what people in authority want you to do. There are all kinds of experiments about that. And scarcity, which is sort of the most straightforward one, is one where people don't think something is valuable, but they do as soon as they think they can't get it. So Disney does this very well. Disney every couple of years says, hey, we're about to release The Lion King on DVD, and then you'll never see it again. So you've got 2.5 minutes to go online and buy it, and everybody buys it, and then their kids stick it in the DVD player and destroy it or whatever, or their grandkids, and then 5 years later they come back and say, we're going to release The Lion King for 2 minutes, and you'll never see it again, and it works. Sales. How many of you people have gone into? This kills me. What's it? Black Thursday? Black Tuesday? Is it Tuesday? Black Friday. Black Friday, right? The day after Thanksgiving. Lines around the block, and for what? Because it's a sale. You should wait till after Christmas, right? It's actually, the prices go down, but you can't do that. It just doesn't feel the same because there's not scarcity. Scarcity works. And by the way, you know what's really good about scarcity and what's good about all of these things? I can tell you that it's about to happen, and you'll do it anyway. You can't help yourself. There's all these great experiments that people have done where they've shown that people have these habits of doing certain things if they aren't thinking. And even if you explain to them how to do it, what you're doing to them, they will try to overcome it, and they might, but if you get them to do something like count backwards from 100, they slip back into doing it again. Basically, it takes an enormous amount of effort on your part to overcome these kinds of things, even when you know that they're happening, even when you're trained in seeing them and recognizing them. So we're going to implement that. And we're going to build our murder mystery. We're going to build our little story. And we're going to use these kinds of techniques in order to get you to do what we want you to do, to go through that door as opposed to another door. And I won't go into too much detail in this, but basically we ran a couple of studies, involved a couple of hundred people. We did a couple of different choose-your-own-adventure style things. And we said to people, play these games. And for some of those people, we just let them play the game. And for other people, we tried to influence them by adding little sentences here or there that suggested scarcity, or little sentences here and there that accepted they should reciprocate. And so you had little video games like this. We'd walk around. This is a story about someone who's walking through Japan and various things, and you're trying to get him to buy fish before he goes home. That's all you care about. And no matter what happens, whether he buys fish or not, in the end he meets a dog and they go home and they live happily ever after. But you want him to have bought fish. And there's no particular reason for him to buy fish. And so you put these little things in the middle that says, you know, if you wait too long, you won't have a lot of choices on the fish. And some people you tell that, and some people you don't. You don't highlight it, but that's the sentence. That's the difference between the control case and the experimental case. And you do the same sort of thing with this other story where you kind of ask people to, you know, spend a little bit of time with you to sort of reciprocate on something. And you run these experiments. And you test some people and you try to influence them, and you let other people go without influence. And you do this all automatically. Right? So this isn't a person sitting down and behind the scenes doing this. You let the machine do this and let the machine figure out when it should try to do the influence, when it's going to be most effective. And it works. It not only works, I mean, this is the thing that I like about it. The players interact with the story. So we actually got hundreds of people to play these games, which is very difficult to do because they weren't the most exciting games in the world. We use very simple text statements to actually get them to do things that they wouldn't do otherwise. And if you ask people, we surveyed them, if you survey people afterwards, they all say they're in control. And in fact, the people you tricked into doing the thing you want them to do actually report being in more control than the people you didn't. And meanwhile, you get all kinds of data. And it turns out some of these things work better than others. Now, depending upon who you are and your background and whether you like me or not, you might think that I'm evil, right? Because I'm building a system that's now going to trick you into doing something that you didn't actually want to do. And I submit that sure, I'm evil, but actually, you know what? The world is a better place because you got that fish, or because you did the murder mystery as opposed to the horror story, and you didn't know any better, you were happy. And that's okay. And by the way, you do it to each other all the time. I mean, it's the way you work with one another, and that's okay. So what did we end up with? What we ended up with is something that collaborates. Now, I didn't tell you all the details. There's a long story. I actually give a talk on each of these things separately, and each one's an hour. But there's a lot of stuff I didn't tell you. But what we really ended up with here is something that collaborates with an author, someone who wants you to do a murder mystery on the one hand, works with that person the way people would work with one another in some sense to build a story, and collaborates with the player, the person who's a part of that story. And by playing that sort of intermediary between those two people who never meet, it creates an immersive and adaptive experience. It learns over time how to interact with the person, and it learns over time how to interact with groups of people just by observing the data and building it, just the way that Cobot did, and by understanding something about humans. So it cheated in exactly the same way that we cheat. We get through by making assumptions about the environment, which clearly Cobot made, and clearly the drama manager, the interactive fiction, made, and by making assumptions about people and how they interact with one another and taking advantage, in a good way, of those assumptions. And we did it by not just by understanding something about humans, but by combining not just the mathematical tricks that I didn't go into detail with, but I flashed up on the screen, a little bit of machine learning and adaptivity, but also human-computer interaction, psychology. We stole a little bit from the marketing literature, and so on and so forth. And that's what it took to build a kind of system like this that can interact with other intelligent beings, some of whom might be human. Now, the goal there, again, to get back to the very beginning of the talk, and my very last slide, is I wanted to give you just a taste, just a hint, that it's possible to build these systems. Socially smart systems that can adapt over time, can interact with one another, and can learn to live with us in such a way that is interesting, such a way that we might all find useful, even if they're tricking us into doing the right thing. And so I'm going to leave you with that thought. It's a good thought. I'm going to leave you with that thought that we are very close to building these kinds of systems, and over the next 10, the next 20, the next 30 years, we'll have more and more of these things, more and more stories built collaboratively with intelligent machines, more and more cars that aren't just driving you, but are driving with you, are living with you, are aging in place with you, and so on and so forth. I like that idea anyway, and I hope you will join me afterwards. We can talk about it a little bit more. Thank you for your time.